Hi everybody, Mrs. Pesic here. We are looking at section 6.3, vectors in the plane. Your learning objectives are to represent vectors as directed line segments, write the component form of vectors, perform basic vector operations and represent them graphically, write vectors as linear combinations of unit vectors, find the direction angles of vectors, and use vectors to model and solve real-life problems. So let's start with a little introduction here. Force and velocity involve both magnitude and direction. So you need to have a direction that you're heading, and you need to know how far you're heading or what the speed is, that kind of thing. So they cannot be characterized by a single real number. You need a directed line segment. A directed line segment has an initial point P and a terminal point Q. Its magnitude, or its length, is denoted with these vertical bars here, like this, and it's read the magnitude of vector PQ. Okay, and you can be finding the magnitude by using the distance formula. So two directed line segments with the same magnitude and the same direction are going to be equivalent. Vectors are represented by lowercase boldface letters. U, V, and W are the most commonly used, but they will be bold-faced when you're naming a vector. Okay, so let's look at this first example. We are looking at example 1. It says, let vector U be represented by the directed line segment from point P, which is 0, 0, to point Q at 3, 1. Let vector V be represented by the directed line segment from point R at 2, 2 to point S 5, 3. And you are trying to show that these two vectors, vector U and vector V, are equal. Okay, so let's start off. It's going to take us 2 steps to do that. Step 1 is to show that the magnitudes are equal. So to show that the magnitudes are equal, that means that we are going to have to use the distance formula to find the lengths of these segments. So I'm trying to squeeze this onto the screen here, and that's not locked together. Let's get that up here. Okay, so segment or vector PQ, to find the magnitude, remember these vertical bars mean the magnitude. All right, that means we need to find the distance from point P to point Q. So we always want to take terminal minus initial, so I'm going to say difference in my x coordinates, 3 minus 0, 3 minus 0 squared plus 1 minus 0 squared. And when we do that, we end up getting 3 squared plus 1 squared, and that's going to give us square root of 10. If I want to find the length then for the magnitude of vector RS, again, if I use the distance formula for the points from R to S, I'm going to take the difference in my x coordinates, so 5 minus 2 quantity squared plus 3 minus 2 quantity squared, and that's giving me square root of 3 squared plus 1 squared, and again I get square root of 10. So what we showed is even if these two vectors have different starting and ending places, they both have the same magnitude, meaning their lengths are the same. Let's actually plot these to see what they look like on this graph. So I am going from 0, 0 to 3, 1 for the first one. So 0, 0 to 3, 1 would be right here, and I'm going to indicate that with this vector like this. Maybe clean this up a little bit. All right, so there's the first vector, and I put a little arrow there, and then I also want to go from, for vector RS, I'm going from 2, 2 to 5, 3. So here's vector RS, goes from 2, 2 to 5, 3. So it looks like this. And the point is, if I can move this vector and it goes right over that vector, I can see that they have the same length. All right. That was only one part, though, of saying that they're equivalent, because not only do they have to have the same length, but they also have to have the same direction. All right. So to find the direction, we're going to need to find the slopes. So if I want to find the slope of this first one, my difference in my y's, remember this is a 0, 0 to 3, 1. If If I find the difference in my y's, that's 1 minus 0. Difference in my x's is 3 minus 0. I get that this vector rs, no, that was pq, that vector pq has a slope of 1, 3. So that's the direction that it's heading. It's heading up 1 and to the right 3. And then if I find for rs here, the slope there, I'm going from 0.22 to 0.53. So again, if I find the slope, difference in my y's over difference in my x's, so 5 minus 2 over 3 minus 2, I end up getting the wrong answer because I did difference in x's over my difference in my y's. But you guys all caught that, I'm sure. 3 minus 2 over 5 minus 2 does give me 1 over 3. So the vectors have the same direction. So since they have the same length and the same direction, we prove that the two vectors are equal. Okay, so what about the component form of a vector? The component form of a vector. If a vector has 0, 0 as its initial point, we say that the vector is in standard position. So in the last example, vector PQ was in standard position. We can represent a vector in standard position just by listing its terminal point v1 comma v2. So this is the component form of vector v. Notice the bold face when you name a vector. And it's going to be written v equals v1 comma v2, which is just its terminal point. But we use these, I'll refer to them as vector braces because they're kind of just these angled braces there instead of just normal parentheses. The coordinates v1 and v2 are said to be the components of vector v. So if the initial and the terminal points lie at the origin, if they both the initial and the terminal points, then vector v would be the 0 vector. So picture your 0 vector. It starts out at 0, 0, and it goes just to 0, 0. So in other words, it's staying right there at that point. All right, and it's indicated by a bold face 0, and it's just written vector with vector braces saying I'm going to the point 0, 0. All right, kind of like going to nowhere. All right, how about the component form of the vector with the initial point P equaling P1 comma P2 and terminal point Q, where the ordered pair is Q1 comma Q2. That would be given by, I should say, vector PQ is going to be, you're going to again use these vector braces, and you're going to just take the difference in the y coordinates. So that would be an x coordinate. Difference in the y coordinates, so Q2 minus P2. I'm sorry, you do want the difference in the x's. I'll get it. Difference in the x's, always take the terminal minus the initial, so Q1 minus P1, and then difference in your y's, Q2 minus P2. And that's going to be your vector in component form. The magnitude or the length of the vector, again, you can use distance formula to get that, or if it's already in component form, you can just take v1 squared plus v2 squared and take the square root. If vector v, the magnitude of vector v is equal to 1, then we say that v is a unit vector. And if the magnitude of vector v is 0, we say that vector v is the 0 vector. All right, let's take a look at this example. Find the component form and the magnitude of vector v that has initial point P at negative 2, 3 and terminal point Q at negative 7, 9. So let's get a little picture of what's going on here. Okay, so let's get a little visual of what's going on here. We have the initial point is at negative 2, 3, so that's right here. That's point P, and it's going to negative 7, 9. Negative 7, 9 is going to be right here. So my vector PQ is going to look like this. All right, there's my vector PQ. And at this point, if I want to write it in component form, all right, for vector v, making that bold face, I'm going to take difference in the difference in the x coordinates So -7 minus a -2, comma, and then I want difference in the y coordinates. Again, terminal minus initial. So it's always got to be 9. Well, in this case, it's going to be 9 minus 3. So my vector v, boldface, is going to be -7 plus a +2 is a -5, and 9 minus 3 is 6. What this is saying is that it is equivalent, the vector PQ is equivalent to starting out the same vector. Trying to make a little copy of this and paste. All right, it's the same thing as taking this vector and sliding it right here with its initial point at the origin and having it end up at -5, 6. Well, it kind of does. My line is a little bit off. But that would be -5, 6 would be this point right there. And let's see, there was more to this problem. We were also going to find, we found the component form, but now we need to find the magnitude. So to find the magnitude, remember we use those double bars like that, and we really just need to take -5 squared plus 6 squared and take the square root. So we get 25 plus 36, and that gives us 61, square root of 61, and that would be the length or the magnitude of the vector. All right, let's talk about vector operations. There's scalar multiplication and there's vector addition. When we multiply a vector by a scalar, that can be thought of as changing the length of the vector. If the vector is negative, we are changing the direction to the opposite of what it was. So let's take a look at this example. If we have vector v as 3, 4, notice the vector parentheses, if you will, and so we have vector v is going to start at 0, 0, and it's going to go to the point 3, 4. So that's right here. And so that is going to just look like this. So there's my vector. And then it says, now try multiplying that vector by the scalar -2. So I'm really taking -2 times the vector 3, 4. And that's what gives us -6, -8. So if I find -6, -8 on my graph, that's the order, this is the order pair 3, 4. This is -6, -8. And if I draw in this vector, it's going to look like this. So not only is it twice as long, but it's also going in the opposite direction. All right, to add two vectors geometrically, position them without changing the magnitude or the direction so that the initial point, let me fix this typo here. So the initial point of one coincides with the terminal point of the other, and the sum of vector u plus vector v is called the parallelogram law. So let's see how this works. And also u plus v would be called the resultant of vector addition. So do I have an example? Yes. No. Definition of vector addition and scalar multiplication. Well, let me back up for this for a second. So if we have, let's say vector u is going to be, let me make that boldface, is let's say that's going to be 2, 5. And let's say vector v is going to be 6, 1. All right. Then if I do vector u here, 2, 5 is going to put me right here. So there's the initial point. There's the terminal point. Let me draw that in like this. That's my first vector. That's vector u. Whoops. Vector u. And now let's draw in vector v. Vector v goes from 0, 0 right here to, let's 6, 1. 6, 1 is right here. So if I draw in that vector, that vector is going to look like this. There's 6, 1. But to add these vectors, u plus v, I'm sure that you could figure out how to add them, you know, just adding the x coordinates 8 and adding the y coordinates 6, and we'll get the sum of the vector u plus v, boldface, would be 8 comma 6. But how can we get that using the geometrically? You would position them without changing the magnitude or the direction, so the initial point of one coincides with the terminal point of the other. So for example, I can take this vector here. Didn't want to move that. I can take this vector here, make a copy of that. That's that same vector, right? That's my vector v, but I can take it and I can put it right here so it's at the, so its initial point is at the terminal point of view. All right, if I do that, then when I close this up with making another copy of vector u, all right, there's my vector u. When I put them together like this, I am forming a parallelogram. And then if you look at the vector formed from the initial point to across the way, right, to where it's ending up, that should be our 8, 6. And sure, it's pretty close there. That's our 0.86 there. Right? So it gets right here to 0.86. So we can see this geometrically, or you can, of course, work it out with a little arithmetic. Okay, so this is just saying here, definition of vector addition and scalar multiplication. If you have vector u, which is u1 comma u2, notice our vector parentheses, and vector v is v1 comma v2 in vector parentheses. If those are vectors and k is some scalar, then the sum of u plus v is going to be the vector u1 plus v1, add those x components together, and u2 plus v2, that's adding the y components together. And the scalar multiplication of k times vector u is going to be k times vector u is just going to be, just multiply through and get k times u1 comma k times u2. All right, and then the negative of vector v is same idea. Think of your scalar as just like a -1 times that vector v. So you're multiplying -1 times your vector v1, v2, and you would end up with opposite of v1 comma opposite v2, again in vector parentheses. What if we're subtracting? Same idea. You would subtract the x components, subtract the y components. All right. And I'm going to skip that part. All right, let's go to this example. If we were going to find, if we were going to let vector u be 1 comma 2, so that's going from 0, 0 to 1, 2. That's this vector right here. And if we want to then have vector v be 3, 1, 3, 1 is right here. So that vector is going to look like this. Then you can, I'm going to have you finish this up. You're going to find the sum of those vectors, and you're going to draw it in graphically. All right, so use the graphical method, geometrical method, and also check it with algebraic method. Then find u minus v and 2u minus 3v. You can pause this video to do this and then go on to the next step. Okay, let's now talk about what a unit vector is. A unit vector is a vector with a magnitude of 1, and it is often helpful to find a unit vector that has the same direction as a given non-zero vector v. So to do this, you're going to divide vector v by its magnitude to obtain the unit vector. And we often call the unit vector vector u, boldface u. All right, so for example, if we have vector v, which is, let's say, the vector 2 comma 5, that is That is this vector right here, 2, 5, and the unit vector would be the vector that goes in the same direction, but it's just this little guy right here that only has a length of 1. All right, so if we wanted to try and find that unit vector for this particular example, let me give myself a little bit of room to work. We would say we would have to first find the magnitude of vector v, which is going to be square root of 2 squared plus 5 squared. So that gives me 4 plus 25. That's the square root of 29. And then the unit vector, vector u, would be 1 over that magnitude. So that's 1 over square root of 29 times my vector, which was 2, 5. And so I would end up getting 2, if I distribute that scalar into both of these, I would get 2 over square root of 29, 5 over square root of 29. All right, and if you want to simplify the radicals, you can multiply by square root of 29 over square root of 29 here. Same thing here, and we would end up with 2 square root of 29 over 29, 5 square root of 29 over 29, like this. That would be our unit vector. I'm making that a boldface U. All right. Well, and we're supposed to verify that that actually has a magnitude of 1. So if we were going to try and verify that that had a magnitude of 1, let me get this on another page so we can do that. All right, so got a bunch of stuff here, but if we were trying to find the verify that this was actually that the magnitude of vector u is it really equal to 1, then we could find the magnitude by taking the square root of 2 rad 29 over 29 squared plus 5 rad 29 over 29 squared, and we want to show that that's actually equal to 1. Well, I might not appreciate having this in rationalized form, so I might want to just leave this as 2 over square root of 29 squared plus 5 over square root of 29 squared. I think it's going to be easier to see if that's actually equal to 1 or not. So if I square the 2, I get 4. If I square the square root of 29, I get 29. And over here, I get 5 squared is 25. Square root of 29 squared is just 29. And sure enough, that is 29 over 29, which is 1. And the square root of 1 is equal to 1. So it does work, and we did find a unit vector. All right. I thought there was an example for you to do. Oh, here. Find a unit vector u in the direction of 7, negative 3. This is just a worked out example here for you. Square root of 7 squared plus negative 3 squared turns out to be square root of 58. So you get 1 over square root of 58, which is getting multiplied then by the vector 7, negative 3. So here's our unit vector right here. And you can verify that it is just equal to 1 by, that the magnitude is equal to 1 by taking the square root of each component squared. And it does work out to be 1. All right, let's talk about unit vectors. The unit vectors 1, 0, and 0, 1 are called the standard unit vectors, and they are denoted by boldface I and boldface J. So what are these? Boldface I is just this, I'll use blue for boldface I. So that is just a vector that starts at 0, 0 and goes 1 unit to the right. All right, and the idea is we may want a combination of these, like we may copy this. So I may want to put 2 of them together or 3 of them together and so on to see if I put 3 of those standard unit vectors together, I would actually have the vector 3, 0. And same thing with vector j, boldface j here. And vector j is the vector that's 0, 1, so it goes from 0, 0 up to 0, comma 1. And again, I might want a combination of those. So I might want to have a few of those. Right? So there's putting two of those together. So don't confuse vector I, boldface I, with I, the imaginary unit. I know we haven't really talked about that yet, but we'll get to the imaginary unit more in chapter 2. So vector I and vector j can be used to represent any vector v1 comma v2, where you take v1, whatever that component was, and multiply it by the vector I, which is 1 comma 0, and you take v2, that was the y component, and you multiply it by vector j. And you get a linear combination of the unit vectors I and j. Let's take a look at this example. Let u be the vector with initial point -2, 6 and terminal point -8, 3. Write u as a linear combination of the standard unit vectors I and j. So in order to do this, I would first write this in component form. So that means I want to write vector u as, I want to take my terminal minus initial, so I'm going to do -8 minus a -2, comma, and I want to take the terminal y minus the initial y, so it's going to be 3 minus 6. So I get that this is going to be -6 comma -3. That is the component form of vector u. And if I want to write this as a linear combination of the standard unit vectors I and j, then I'm basically saying I want -6 of these unit vector i's, and I want to add to that -3 of the unit vector j's. So this is how I would write that. And if I can have a graph to kind of demonstrate this, I do have this graph. So if I want to, actually I want to get this graph down below. Okay, so on this graph, I want to plot -2, 6 and -8, 3. -2, 6 is here, and -8, 3 is here. So this vector looks like this. That's not what I wanted to do. All right, there's my vector that goes from -2, 6 to -8, 3. And the standard unit vector of -6i, slide this over, -6i plus 3j is basically saying if I take, what colors did I use for these? Blue for this one. If I take -6 of these, so I take these little unit vectors, 6 of them, but they're all going to the left. So -6 of these unit vector i's, and I take -3 for my unit vector j. So in other words, the j vector goes up 1 unit, but I want to go down 1 unit, but I want to go down 3 times. So this is what we mean by -6i, vector I, and then down here is -3j. So we've written our vector as a linear combination of the standard unit vectors I and j. All right, and here's another example. If we let vector u be I plus j and vector v be 5i minus 3j, what would 2u minus 3v be? Well, I think you get the idea that we could take 2 times vector I plus j, so that's 2i plus 2j. This is going to be my vector 2u, right? And then my vector, I want to subtract off a vector 3v, which would be 3v would be 15i minus 9j, and I want to subtract, so I would end up having negative 13 times my standard unit vector I, and then minus a negative, I would have plus 9, so that's going to be 11j for the standard unit vector j. Okay, and we're going to stop at this point, and we'll get into direction angles next time. So at this point, you have some additional work to do for this assignment.